I don't know. It might have turned something off in the time I just been sitting in the car. And I was like, it's not
Do it. Oh, didn't see you there. Hi guys, welcome back to the Science Planet. I am your host, Dr. and I was just doing some minor calculations. Jojo, my boy, could you erase this as you always do? Come now. While he's getting ready, I just want to give this shout out. Thank you for 57.4 thousand subscribers. It's a big milestone. Be sure to smash that subscribe button, like the video, share with a friend. Go to all my socials, join my Patreon for early. Hurry up, now! Hurry up! You know, subscribe to my socials. We have an Instagram, a Twitter, a Facebook, MySpace, a Discord server if you want to join, and we can talk about all sorts of other scientific collaborations. And that's about it. So once he's done, we'll get into the main lesson of the video. This is Professor Cornell here. I don't know where I am. Went so horribly. No. Hey, start.
Hey guys, DNA Dan here, and on today's episode we will be learning about DNA and RNA. Hey, that's the namesake of the channel. Would you look at that? So what is DNA first of all? DNA is basically responsible for gene transfer. The attributes you get from your mom and your dad, DNA is responsible for that happening. And it's also responsible for helping to make RNA. RNA is used to make things like, hold on, let's move the camera just a tiny bit, is used to make things like proteins and all sorts of other organelles in your body. Okay, so now let's get into what makes up the nucleotide for each of these. Okay, just had to see if it was working or not. So first we have the pentose sugar right here, which connects to the nitrogenous base as well as the phosphate on the back. We'll get into the specifics about all those later, and each carbon around the pentose is also labeled. So we have 1 prime, 2 prime, 3 prime, 4 prime, and you may not expect it, but also 5 prime right in this area. The proper way to write it to draw would be as if it was bent, and this is where the 5 prime is, but for simplicity's sake, we draw it like this. And also, let's get into why they are called DNA and RNA. So, DNA stands for deoxyribose nucleic acid. The Na is nucleic acid, of course. So, what makes it so special is it is just attached to an H carbon right here on the 2 prime. Sorry about that, opened my windows. RNA, meanwhile, a little bit different. RNA just stands for simply ribose. Okay, and it isn't attached to just a hydrogen on its 2 prime carbon. It is actually connects to a hydroxyl group of OH, hence why DNA stands for deoxyribose. It doesn't have an oxygen connected there, unlike RNA. Okay, now we will get into why the nitrogenous bases and the different varieties they come in. So there are 4 different types of nitrogenous base can be in DNA and RNA. The first is adenine, then thymine, guanine, and finally cytosine. Cytosine. What you may notice about all of these, right, is that I've, color coded them, and they sort of have these complementary shapes. That is no coincidence. That is deliberate, because adenine actually connects to thymine, and guanine connects to cytosine. This is why in a double helix, the little bridges in between a DNA drawing, those little connections are these guys connecting with one another. And of course, I've color-coded them so that you know that adenine only connects with thymine, and guanine, of course, only connects with cytosine. This allows them to function as a sort of code. So you see this little sequence of the 4 A, T, G, C, T, A, A. This could code for anything like hair, eye color, things like that. It code for some, like, having more hair on your legs or ankles, I guess. So it's very versatile using this system. Okay, quickly going back to having the the prime numbers on all the carbons, we need to get back onto why that is important. So obviously, first off, the 2' is important because what distinguishes DNA and RNA. 1' is important because it connects to the nitrogenous bases. However, 3' and 5' are also important because they allow the nucleotide to connect with one another, as seen right here. So as you can see, the 3' connects with the phosphate of another nucleotide, and the 5' is what allows it to connect with a 3' because it's connected to the phosphate, of course. The way they connect with one another is via a condensation reaction. Also, the direction in which they're going is also important. Now let's look at an RNA chain right here, and I'll tell you why the direction they're going is important. So as you can see, they're going this way, which, given this, makes the code GTTAC, or GTAC, right? However, if you were to simply just flip it, make it go the other way, it is now CATTG, or KTTK. So directionality is very important because we're working with very specific codes that can either make a protein, it could mean vastly different things. Okay, let's take a model like this and help you identify. Let's choose green for this because I already chose purple here to help you remember this. So always remember that the little bottom corner one will always be 3', and this will always be 5'. And as you can see, it'll just connect like this and like this, and for its complementary side, it'll be in reverse. So it'll be 5, and then it'll be 3, and then it'll be 5, and then it'll be 3. And you get the idea. Let's get into the bonds that make up DNA. So first we have the covalent bonds, which are just everywhere. You see them here, see them here, you see them here. They're what combine the nitrogenous base to the sugar with the, how the sugar makes itself. The sugar connecting to the phosphate connecting to the other sugar or nucleotide. And then we have the hydrogen bonds between two nitrogenous bases right here, and right here only. So there's two types, the covalent and hydrogen bonds that nucleotides, make with one another or themselves. And finally, let's get into the structure of DNA. The way I see it, or the way it's most helpful to me, is to kind of think of it, because DNA is in a double helix shape. Think of it kind of like a revolving staircase of sorts, the way it just continuously goes up in one direction. An easier way, in my opinion, than that, think of it as two little strings of rope, identical strings of rope that are just going in one direction and another direction. And you take those, you draw little rungs like a ladder, and you just twist them in opposite directions at each end. And that right there is your double helix, and that is how you get the DNA structure. It's anti-parallel structure, I should say. And that's about it. Follow for more DNA related things. I have been DNA Dan. Like and subscribe. Goodbye.
Yes, sir. Yes, I'm hungry too.
Aren't you gonna say subscribe?
Like and subscribe. Smash that like button. Smash the
Okay.
subscribe button.
Or
We're trying
what?
to get to 60K. Science
Okay.
Planet. Professor Cornwell.